All right, guys, so today we have a short clip with Dr. Nicholas Ratamess, a former mentor and professor of mine. He is the editor-in-chief of the Journal of Strength and Conditioning Research. He has a ton of publications in the field. He's very well known in the field, but doesn't have a huge following as far as Instagram and YouTube fitness because he hasn't really put himself out there. So I really wanted to get this recording done so that people could really see his experience and what he has to offer in the field. Today we're going to have a short primer on signaling for muscle growth. All right, guys, so we have Dr. Nicholas Ratamess with us today. I'm fortunate enough to be a guest in his house, and he was actually a professor of mine for a while back at the College of New Jersey, so welcome, Nick.
Yeah, David was one of our best students, obviously, as you can tell.
So you just recently had a conference, right? Could you just give a little explanation of what that was?
Well, I went to two conferences recently, the ACSM National Conference, which was in Orlando last month. I did a talk there on testosterone signaling. It's part of a big symposium that Dr. Bill Kramer put together. We were looking at growth hormones, the superfamily of growth hormones, testosterone signaling, cortisol. Dr. Marin Fabrala did a talk on that. And then Dr. Brad Nindle gave a talk on IGF-1. So that was a good conference. And then I just got back from the National Strength and Conditioning Association conference in Washington, D.C.
Yep.
So busy month.
Yep. And so actually a lot of the people I've had on recently that I've been interviewing, like Michael Roberts, Cody Hahn, and a lot of these people know Dr. Ratamess. And it's kind of funny, I was talking with somebody about this, how when somebody was your professor, I feel like it's always still like Dr. Ratamess, at least like in like a formal setting, you always just think of them in that way.
I still call all my former professors doctor.
Yeah, it's just something about it. But, so Dr. Ratamess knows a lot of those people and vice versa. And you are actually, in the last year and a half, you became the editor-in-chief of the Journal of Strength and Conditioning Research, right?
Yes.
Which is a pretty big deal, and you've been on how many papers now?
About 190 plus, 193.
Yeah. So, again, a huge name in the field, and I think it just kind of goes to show that the top researchers, this doesn't just apply to this field, but a lot of fields, the top people aren't necessarily who's famous on Instagram, and there's nothing wrong with being famous on Instagram, but just because somebody has a huge following doesn't necessarily mean they know what they're doing, and just because somebody doesn't have a huge following doesn't mean that they're not an expert in the field. And just talking to Nick for the last hour or two, he's a very intelligent guy, and obviously from all the classes I've had with him, very intelligent guy, really knows this stuff very well. And and just to be clear for everybody, obviously huge name in the field now. You've done a lot, and actually you were on the what was it with Brad Schoenfeld?
His dissertation,
yeah,
looking at resistance training.
Okay, right. So everybody does know Brad Schoenfeld now, but actually Dr. Ratamess here was kind of like overseeing some of the stuff that he was doing.
Well, I was on his committee. Brad did all the work. He did.
Yeah,
job,
right.
But
just one more example. But you walk the walk, right? So lifetime PRs. Could you say for like the big three: squat, bench, deadlift? What you've done?
About a 650 deadlift, 630 squat, and about 430 bench. Drug free. It was all drug free.
Right. So yeah.
Make sure that mentioned. Don't edit that out.
Right.
They're not that impressive for a drug athlete, but
right. No, for a natural athlete, it's crazy. He's super strong, super big guy. You can see his arms popping out of his sleeve right now. So very impressive guy. And again, thank you for coming on talking today.
No problem, Dave. Anytime.
So could you get a little, while we were driving, you were talking about recently there's been some people have kind of like, I guess, shoot away the idea of testosterone being a signal for hypertrophy, and you don't quite agree with that. Could you just explain the controversy there?
Well, testosterone certainly is a very potent anabolic hormone. I think most would acknowledge that it is an anabolic hormone. Where some of the discrepancies come in over the years is that the acute response to resistance training has been questioned as to how much of an effect that has on the potential muscle hypertrophy and performance increases that take place after that. Some will say 0%, okay? Most likely not 0%. How much of a percent? It all depends on the individual. It's very hard to say because testosterone, the whole signaling, when you look at how testosterone works, it's basically, at least so as we know now, part of at least 7 signaling pathways. When you think of all the potent anabolic intramuscular signaling pathways in skeletal muscle, testosterone is directly or indirectly involved with those. It's involved in satellite cell proliferation and differentiation as well. There's genomic, non-genomic signaling. Matter of fact, non-genomic signaling now has the ability to increase intramuscular calcium, which some have speculated might even help with acute performance. Again, there's not much research on that,
yeah,
but it's being implicated for so many different things that, I think it's pretty safe to say having 0% effect is not realistic.
Right.
But how much, whether it's 10, 12, 15, who knows? It really depends on the individual. But really, sometimes we wrote a review paper back in the day that often gets cited on that. But 15, 20 years ago, all of the data we had on resistance training was looking at circulation. Matter of fact, in the talk I just did, I threw up a slide there and said, it's almost like the outside looking in.
Yeah. Whenever
you look at an area of research, you start with the most basic and then get more cellular. And all of the initial studies back in the day were looking at circulating concentrations in the body, whether it was resting, whether it was acute response. Matter of fact, most of the acute response is not because you're actually producing more. In males, it takes probably at least 25 to 30 minutes to produce new testosterone from LH signaling in the brain. Most of the studies are less than 30 minutes when you look at the acute response anyways. Plasma volume reductions as well as reduced clearance during exercise are pretty much the main reasons why you have that acute elevation.
Really? Okay.
So you really have to look at that. That's just part of the signaling process. Then certainly testosterone has to bind to receptors in order for it to be effective. We look at then the field started going to what's happening with the receptor. Upregulation, downregulation. We know within 2 to 3 days following a workout, there's usually going to be some specific significant upregulation that's thought to enhance the signaling process and its transcriptional activity. Okay? Now you look at that androgen receptor, and there are a number of things. Its phosphorylation state has been studied a little bit here and there. Okay, even genetic elements on the actual. Some individuals are more even responsive to testosterone based off of how many repeats there are within the actual sequence of the testosterone and the androgen receptor protein itself. Once the androgen receptor bound to testosterone makes its way into the nucleus, then it's helped by a lot of co-activator proteins and it's inhibited by some co-repressors. That whole positioning right there is a key area. That's where a lot of the potency is.
Yeah.
So really, if you want to examine how effective testosterone is, you have to really examine the whole signaling pathway, not just how much is in the blood or anything like that. You really have to be looking at everything it's doing because it's involved in so many things inside skeletal muscle.
Which is interesting because that's kind of what you said before. We were talking about the papers on ribosomal biogenesis, and you were saying how they're trying to put a certain percentage on it, and it's interesting research perhaps, but that it's hard to do that, or the same thing with satellite cell proliferation or anything like that when they're all
interrelated.
Yeah, I mean they're very. It's very
There's
hard to separate.
There's crosstalk between all these anabolic signaling pathways.
Right.
So that makes it hard to try to put a percent on. And again, I applaud the researchers who are trying to do that, but it's very difficult to do because everything's interrelated and everybody has a little bit different physiology. It's hard to really put percents on that.
Yeah, you mentioned the collinearity there, and I think it is interesting. I know their more recent papers did show that ribosomal biogenesis was significant, but maybe other factors are affecting that. So, how do you weed all that out?
Well, that's where the proteins are being put together. Ultimately, it's protein synthesis, how much proteins you're synthesizing when it comes to anabolism. So you look at all the train, along this chain. And even though you take males, LH is the main signaling hormone that's released that causes steroidogenesis in the testes, but there are neuropeptides that have been identified over the years, like the kispeptins. The kispeptins are one group that will cause the release of LH from the.
We got a cat over here.
Yeah, edit out the cat. But will cause LH release, which then is certainly going to lead to testosterone steroidogenesis. So what's affecting those neuropeptides? Exercise hasn't really been studied much. Obesity has a little bit. We know obesity reduces testosterone.
Right.
But what's happening all the way along? That's the interesting thing. It's probably too simplistic to try to just look at a circulating level.
Yeah.
You really have to look at everything that's going on to try to.
Yeah, and it's interesting to hear, actually, I had not heard that before, that a lot of the, since these studies are so short-term and like 30 minutes, where that increase in growth hormone, testosterone, cortisol, like that might...
Well, GH, you can... See, GH is stored in somatotroph cells.
Yeah.
And it's released in pulsatile bursts. You produce more when you work out GH. And GH is really an aggregate of many different, over 100 isoforms now that really aggregate together to form multiple levels of molecules that have different levels of biological activity. But T, it's a steroid, so it's produced and released.
Yeah.
So the timing, unless you're doing a longer workout, which hasn't really been looked at much there, Do you actually produce more? I mean, in studies we've done, if we've corrected the values for plasma volume reductions, you see the normal diurnal pattern.
Yeah.
The question then becomes, all right, well, why is there acute elevation? Is there some kind of significance to this? Well, imagine you're working out with weights, now you get blood flow increase to muscles. So if you have an artificial elevation, and that's why I like to use the term elevation, because sometimes you use the term increase, it implies that you're producing more.
Right,
You're really
right.
not. You may not be. So you have that elevation now. If you have that acute elevation, even if it's from plasma volume reduction, that's thought to help drive testosterone binding to its receptor, given the fact that you're going to have greater blood flow to muscle during the workout. Now, again, that hasn't really been studied. That's just been theorized. But again, the hormone itself is the signal that creates the cascade intramuscularly. So,
right. And do you think these methods that we're studying now are going to be, anytime in the near future, able to be manipulated in order to, I mean, obviously a lot of the research, there's not a lot of money in getting people bigger. A lot of it is
it's all clinical. That's where the money.
Right. Yeah. But still, I'm sure at some point, even just like bodybuilders and stuff are going to be looking for ways to kind of manipulate these things in order to gain more muscle. Do you think that's on the horizon?
Yeah. Well, one of the points I made in the talk I did at the ACSM was that when you look at the nuclear level, that's where these co-regulator proteins are. I think that's the next level of research, because we know even with skeletal muscle, microRNAs have been studied the last 10, 15 years quite extensively. Some of these microRNAs are affecting androgen receptor binding capacity. They're actually co-regulators of androgen and androgen receptor binding to the androgen response elements on DNA. So I think that's going to be an area it's interest. I know some companies now are looking at some of these co-regulators as a target of drugs to treat men with prostate cancer, anti-androgen effects.
Yeah.
Right? So not just blocking the testosterone from the source, but blocking it at the transcriptional area, which again is going to negate the effects.
Right.
So usually if something's going to be done in a clinical sense, it won't be too much longer until some performance element might be studied after that. So I think that's a hot area of research.
Yeah.
I'd like to see more individuals get involved in looking at how those co-regulator proteins are being changed, not only by androgen concentrations, there's only a few studies looking at that, but just training in general.
Right. Very cool stuff.
Because I mean, let me speculate.
Sure.
If you train consistently, and if you have the ability to upregulate some of these coactivators, technically then that could increase the potency of testosterone without even affecting the testosterone production.
Yeah.
So again, you have to look at the whole signaling pathway, and I think there's a bright future there for a lot of research looking at. When I did my dissertation back in 1998, around there, 1999, there were about between 30 and 40 known co-regulators of an androgen receptor binding at DNA. Now, depending on how you define a co-regulator, there's more than 300.
Yeah.
And I think we're just going to continue down that road, even find more.
Yeah.
But then their actual role that they play as a function of training really needs to be studied.
Right.